We are Team A1 FireAway, and this was our capstone project. Our team wanted to create a system for firefighters that would make it easier for them to know the locations of fires. We wanted to focus our project on fires because places like California experience thousands of fires every year, spanning hundreds of thousands of kilometers. Because of this, we decided to create a wireless sensor network that would help with the detection of wildfires. We wanted our system to have fire detection accuracy, fast notification time back to the firefighters, and have a system that would require low maintenance. Because of that, we set the following use case requirements. We wanted our system to have 90 to 95% accuracy when detecting the locations of fires. We wanted the web application to get notification of the fires within 30 minutes, and we wanted to ensure that the system would only require maintenance once a month.
This is a block diagram of our solution approach. We used a Raspberry Pi as our gateway. It was responsible for initiating all of the protocols and also hosted the web app. Our network consisted of 8 nodes. Each node had a Nucleo with an STM32L4 microcontroller, which is designed to be low power. The node also had a LoRa transceiver for wireless communication, as well as a temperature sensor for fire detection. The transceivers are also designed to be low power, as well as long range. All of the nodes are powered with 9-volt batteries. This is our gateway. You can see the Raspberry Pi. It also is connected to a LoRa for wireless communication, and this is our reset button to ensure that all nodes start the protocols at the same time. This is one of our nodes. You can see the Nucleo board with our low power STM, which has built-in low power modes that we used in order to consume as little power as possible. You can also see the red LED we used to show when the node was receiving packets, and the green LED, which showed when the node was transmitting packets. This is our temperature sensor. In a real-world scenario, you would want a more sophisticated method for detecting fires, but for the scope of our project, we used a simple analog temperature sensor.
Here's our web application. We have an About tab explaining our project and a How to Use tab explaining how the application works. Our main visual interface is our map. The map shows the overall topology of our network, which will be used in the test run shown later in this video. The dark blue marker with a home icon represents our gateway router. The 8 light blue markers represent our nodes. As you hover over a marker, you'll see their longitude and latitude coordinates. If one of the nodes was to be heated, the marker would turn red and have a fire icon, as shown in node 8, and a pop-up window showing that the fire is at that location. If a node was to go offline, it would turn gray, and its links to its neighbors would also turn gray to represent them as being unusable links. All the lines represent nodes that are in range of one another. The black lines between the nodes represent active links in our spanning tree, and the gray lines represent inactive links in our spanning tree.
A network protocol stack is used to minimize power consumption and ensure efficient data collection. In the first phase, spanning tree protocol reduces the initial mesh topology to a spanning tree topology. In the next phase, nodes iteratively send link state advertisements across the spanning tree to their child nodes and aggregate the responses from these child nodes, propagating them back to the gateway router. Once the gateway router has the entire tree topology, it can create a transmission and reception schedule. So the next phase involves distributing this schedule as well as a time synchronization boundary to which all nodes will wait to reach before beginning the data phase. This time synchronization is required because some nodes will receive their schedule before others. So all nodes will begin data phase at the same time and execute the global schedule. After which, they will transition to a low power mode. And in this low power mode, they will wait until the 30-minute mark, and then they will exit the sleep state and begin protocol stack next iteration. So here we're resetting all the nodes, and this begins a timer for each node, which allows them to be installed within that time span. So the initial topology is not shown here. It has not yet created the tree. But the mesh topology is shown on the right. So in the spanning tree protocol phase, each node transmits their time slots, with lower address nodes broadcasting first. After this phase, the tree shown on the right will be created. But for now, all links, even the inactive ones, are active. Okay, so now we're in the link state advertisement phase, and the topology seen on the right has been created. The gateway router begins link state advertisement phase by sending out the first request packet to a sensor node, which then forwards these requests iteratively to their children nodes, gathering responses from them, and then sends the aggregate response back to the parent node. So forth, the responses are able to propagate back to the gateway router, and the gateway router will have knowledge of the entire tree topology, shown on the right. It's important to note that we're using a stop and wait protocol using acknowledgements and retransmissions to ensure recovery from dropped packets or CRC errors. It's also important to note that LSA responses are sent in several packets, one per each neighbor, which is one reason why this phase is the longest in the protocol stack. So now the gateway has knowledge of the entire tree topology. It can calculate its transmission and reception schedules for all nodes in the network and distribute the schedule as well as the time synchronization timestamp across the spanning tree. Now all nodes are waiting until the time synchronization timestamp is reached. So all nodes have begun the phase simultaneously. The first node on the top left is sampling its sensor, which is why the heat gun was used to heat that temperature sensor. It transmits that information to its parent node, and other nodes will conduct similar temperature sensor samplings and transmit that information to their parent in the spanning tree. Once all nodes have taken temperature readings and transmitted to their parent in the tree, the gateway router will have knowledge of each sensor's readings and whether they have detected a fire. Because we heated the top left node, that node will appear on the web application as having detected a fire because of the increase in temperature.
We ran 20 tests with an 8-node mesh topology and got an 80% accuracy. This is because for 20% of the runs, the network failed to complete all of the phases. This is mostly due to contention in the LoRa frequency band, which would cause nodes to get stuck trying to transmit or receive packets. This issue was difficult to debug due to the low amount of documentation for the LoRa, as well as the high level of abstraction in the LoRa software. In our tests, the protocols ran in 10 to 11 minutes from the start of STP to when the web app displayed a notification. This meets our requirement of having the web app notify the user of a fire within 30 minutes of a detection. We measured the current of the nodes while they were running the protocols and when they were sleeping between iterations, and calculated that in 30 days it would consume about 35 amp hours. This means that with a 40 amp hour 9-volt battery, we can expect the node to last for 1 month without maintenance.
We would like to thank our faculty advisor Tamal Mukherjee and our TA Adnan Lokandwala for their help throughout the semester. We would also like to thank our professors Sorun Kumar and Peter Steenkista for their guidance. Thank you for listening to our capstone presentation.